it is what it is. That's why I'm doing this testing ahead of time,
Yeah.
That's what you learn from software development. Nothing can fix actually testing your code.
Yeah. All right, so I'm gonna mute myself now again. And then I'll unmute myself after my video presentation.
Yeah.
Okay.
Yeah. So the way we'll do yours, since you want me to play the video, is I'll introduce it and I'll share the screen, play the video, and then when I exit, I'll sort of you'll unmute and take questions.
Okay, sounds good.
And just before we start, one last attempt. Hui Guo, if you are connected, could we do an audio video test for you? I'm not sure if she is around and she's not on the Slack, so that is unfortunate, but we did a video check yesterday, so hopefully it should all work.
I'm here, Pano. Can you hear me?
Oh, okay, great. I can hear you. I can see you. Excellent. I believe you have permission to record, so we should all be set. Perfect. Thank you.
Okay.
Okay. Well, Hans, I think we'll be able to, start in a minute. Basically, more or less there.
Okay. Great.
I guess I'll introduce the session and then hand it over to you.
Okay, that works.
Okay, so welcome back everyone to the second session of FPTalks 2020. Kicking off this second session is Hans Boehm, talking about arithmetic in Google's Android calculator. So Hans, please go ahead.
Thank you. I'll be talking about an arithmetic that was motivated by Google's Android calculator, but has also been used for floating point testing, for testing of floating point math functions. I'll focus on the arithmetic on the calculator application here. So, wait a second. Technical glitch. Why can I not advance the slides?
You may have focus. You might want to exit the full screen and then rejoin it. Yeah, you probably don't have focus.
Oh, okay, something worked. Okay, good. So floating point has the advantage that it's fast. It has a precise definition, but one that's rather unintuitive. So in particular, it's not associative. For example, sometimes even really simple problems generate somewhat surprising answers. If you ask the two most popular web search engines what the tangent of arctangent of 10 to the 20th is, they both agree that it's about 1.633 times 10 to the 16th, though not quite, which is a bit odd. We all know that if we take the limit as n approaches infinity of 1 plus 1 over n to the nth, that should be e. if you try to test this on a calculator, you'll get sort of somewhat consistent answers with that. So for n equals 10 to the 10th, that more or less works and gives a nice answer. For n equals 10 to the 20th, somehow you then get a completely incorrect answer. And we'll actually sort of use that as the standing example here. So what we want for calculator arithmetic really is, as our first goal, is we always want the result to be accurate. We want an error of less than 1 in particular in the last displayed digit, no matter what the computation. And we basically take this as an absolute requirement. It turns out that once you do this, that has some other nice consequences. You can also get scrollable results. So as you'll see here, hopefully, if the technology cooperates. So in order to accomplish that, the candidate solution is to use what's known as the recursive reals, or sometimes the constructive or computable reals. Basically, what you do here is you produce a representation of the exact result, and that representation then allows extraction of arbitrarily precise approximations from that result. This turns out to be almost good enough, but not quite for our application. So since I imagine not everybody may be familiar with this, here's the one slide overview of what recursive real arithmetic is. We basically represent a real number as a function that's capable of producing approximations. So in the really simplified version on the slide here, I give the function an argument n, and it produces a rational approximation that's accurate to 2 to the nth. So the interesting values of n here are usually negative values, sometimes large negative values. So to add two numbers x and y, then we have to compute another function associated with x plus y is just the one that approximates the arguments to slightly more precision and then adds the arguments. And you can do the simple error analysis here, and that's good enough. The actual version that we use doesn't use rational numbers as the result, but scaled integers instead. The rub here is that if you try to compare these, well, there's an obvious way to compare these. You basically have, if given two numbers, you just go ahead and evaluate both numbers to increasing precisions until you can definitely determine that they're different, and you can tell which one is bigger. And if they're not equal, that works fine. The problem is this process diverges for equality. And in fact, it's fairly easy to show that for general recursive reals, equality is in fact undecidable. It turns out that actually equality is decidable for most calculator operations. On the other hand, it's not practically so. There are no known algorithms that actually do this effectively in a way that we could possibly use in a calculator. So the consequences of having these potentially diverging comparisons in the calculator is that, well, even in simple cases, we can't identify domain errors. We can't identify that something is a division by 0. So what will happen in practice is the division itself will diverge, and it'll eventually time out, which isn't completely awful, but it's not good. The calculator can't truncate values correctly, which is annoying because scrolling looks funny if you can't do that. Probably the most serious problem here, somewhat surprisingly, is that if you try to use the calculator to add up your bar tab, you're going to get a strange looking answer that's technically correct, but not what you wanted. You're going to get lots of trailing zeros and the ability to scroll through an infinite number of trailing zeros at the end, which is not really desirable. So what we do instead is, since we can't always get decidable comparisons, but we can actually cheaply get them in many cases, and we actually seem to be able to get them in the cases that people actually care about, we basically provide a way to get those comparisons when we really expect them. So our real type provides an is comparable function to which you give two representations of real numbers. And if is comparable returns true, then you guarantee that the comparison will always terminate, even if x and y are equal. What makes this interesting is that a bunch of classical number theory results basically give you the handle to often return an is comparable value of true. If that weren't the case, this wouldn't be interesting. So the actual representation we use for real numbers is the following. We represent a real number as a bounded rational factor, as a rational number times an arbitrary recursive real factor. And whenever possible, we use a simple symbolic representation to describe the recursive real factor here. This is significantly redundant in that if we just constrain the bounded rational factor to 1, we can still represent all numbers. On the other hand, this potentially gives us a lot more information, which turns out to be quite helpful. We use bounded rationals here rather than general rationals in order to avoid certain performance anomalies if these things get too big. The simple symbolic representation is really simple. It's basically one of the following here. It's the constant 1 or pi. Again, remember that this can be multiplied by a rational number. Or it's one of the small finite collection of functions applied to a bounded rational number. In addition, it turns out we tweak this a little bit to sometimes keep track of whether numbers are known to be irrational. When we operate on these numbers, we try to maintain the symbolic representation of the constructive real factor whenever we can. When we can't, we can always fall back. This representation allows a fallback to just a rational multiplier of 1 and an arbitrary constructive real number. So the core observation that makes a lot of this work is that so long as we have a symbolic representation in this form, we can normalize the number in such a way so that if the number is rational, it's obviously so, meaning the constructive real factor is 1 and it has a symbolic representation that says it's 1. This relies on some, as I said, some classical number theory results. In particular, the Lindemann-Weierstrass theorem is very helpful, and Niven's theorem helps for trig functions. So the consequences here, as far as comparisons are concerned, so long as the number representation includes a symbolic representation, they're either both known to be rational, in which case we can just compare the rationals, or in the other case, if they have other representations, we know that they're irrational, and in general, in the usual case, we can compare them as well, because we can typically conclude based on the symbolic representation that the numbers can't possibly be equal, and thus they can be safely compared by just evaluating to increasing precision. So in particular, if we're comparing a known rational to a known irrational, we know that the naive comparison process will converge. So using this approach, we've used this approach in Google's Android calculator for a while now. It's actually, the implementation is fairly compact. It's about 6,000 lines of code or so. We basically haven't been getting any complaints about the arithmetic implementation, which distinguishes it from an earlier floating point implementation. The only complaints we keep getting is about calculator expression parsing, which turns out to be something that nobody agrees on. It produces results in a perfectly reasonable amount of time for this kind of application. It turns out the symbolic representation actually can be useful at times, so we started to expose that to users under certain circumstances as well. So with this approach, not only can we approximate E in that formula by using n equals 10 to the 100th and get the correct result, we can actually ask how far is that answer off? How much does it differ from E? And if we multiply that by 2, we happen to get an interesting answer. We can, in fact, use larger values of n, and this is sort of near the limit of what will happen, what the calculator will still support on a phone before running out of time. On the other hand, we can still get a reasonable decision procedure which allows us to identify domain errors in the easy cases like this one. So we can guarantee exact answers with standard mathematical properties. We can get arbitrarily precise approximations with decidable equality where it's expected. And the cost for all purposes is not an issue. It actually turns out this is sometimes less expensive than the recursive reals for reasons that are discussed in the PLDI paper that describes this. I think this is actually a good match for arithmetic in general that's directly visible to users. And as I said, we've also used it for floating point math testing. Thank you.
All right, thank you, Hans. I'll take questions, and just a reminder that the way we'll be doing questions here is the raise hand button in the participants window, and you can find that participants button at the bottom of your screen. So I guess the first question will be from Zach.
Yeah, thanks for the great talk, and it's awesome to see such huge impact in the real world for this kind of work. The one thing I was curious about, a lot of times users can't or don't enter the real number they actually want to compute with. They enter some approximation of it. And so I was wondering if you've considered, the problem of trying to detect when, the users entered the first 3 digits of pi or e or something, and, decompile that back up to what the real input they actually wanted was, so you can give them the right answer, and maybe like make an option for it or something. But I'm just curious about that problem.
That's an interesting observation. We haven't tried that. We haven't moved in that direction. One of the constraints with the product calculator like this is that there's usually a lot of resistance to adding additional features unless it flows sort of really, really smoothly as part of the application. In this particular case, I could see that being done well and it making sense, but we haven't really looked into it.
I guess we can do one more question from Santo.
So I have a more pedantic question. So there are, since cost is not an issue, what are the advantages of using recursive reals compared to MPFR with large number of precision bits?
That's a good question. And I mean, there are actually other calculators. I think the Ubuntu calculator does this. It just uses a very large number of precision bits. And basically the difference is that you're investing all the effort to calculate with a large number of bits, whether you need them or not. And there's still a limit. I mean, at some point, things will still go south with the Ubuntu calculator. Though I agree that it becomes sort of fairly difficult to tell the difference in many cases. I think the Ubuntu one uses 1,000 or multiple thousands of decimal digits equivalent.
Okay, great. Thank you again, Hans, for a great talk. Our next speaker is going to be Sangeeta Chowdhary, and she has actually asked me to play a video of a pre-recorded talk due to internet challenges. So I'm going to switch and share my screen. Hans, if you could unshare.
Hello everyone, I'm going to talk about posits and how we can detect and debug numerical errors in posit applications using our approach.
Just to pause here, can people hear sound?
Posits are recently proposed by John Gustafson as a drop-in replacement for floating point. Posits can provide more accuracy and dynamic range for the same number of bits in comparison to floating point. Posit representation is designed to be hardware friendly. Now you write programs using posits and you encounter rounding errors. That's where posit debug comes into the picture. In next few slides, I'm going to show you the approach behind posit debug. We want to detect numerical errors with posit applications. We achieve this goal by doing shadow execution with real numbers. We want posit debug to be usable with long-running applications. Careful design of metadata and compiler instrumentation helped us to achieve this goal by incurring lot less memory overheads in comparison to the other approaches. We want developers to identify the root cause of the numerical errors. To achieve this goal, we provide a directed acyclic graph of instructions to show the error propagation. The key contribution is how do we provide the DEG while maintaining constant amount of metadata with each memory location. Now let me show you how posit debug works with an example. I will walk through this example later on, and details of the program are not important at this moment. Posit debug is based on LLVM compiler instrumentation. Posit values can either be resident in registers or in memory. That means we need to store metadata for variables in registers and variables in memory. For variables in register, we store metadata in the program stack. For variables in memory, we store metadata in shadow memory. Given the variable address, you can get the shadow address from which you can get the metadata. So what should we store in metadata for variables in registers? To perform shadow execution, we want to store the real value, which is used to compute the error by comparing real and posit value. There can be scenarios when shadow value is not available, or we have stale shadow value. We store posit value to reset the shadow value in such cases. To enable the user to diagnose the root cause of the numerical error, we store pointer to the metadata of both operands. Using these pointers, we can generate the DEG of instructions to do the root cause analysis. So the next question is, what should we store in metadata for variables in memory? The way program communicates with memory in LLVM IR is by storing the temporary to memory or loading the memory in temporary. All computations are done on temporaries. When we store the temporary to memory, we store the real value, posit value, and pointer to the temporary that has returned to the memory. The storing pointer to the temporary helps us to trace the provenance of numerical errors within the memory. But there is one problem. What if the stack frame is deallocated? Then pointer to the temporary in shadow memory metadata is a dangling pointer, and we need to check if it is safe to access this pointer. That means we need to ensure temporal safety of all pointers in the metadata space. We use the idea of lock and key from sets proposed by Nagarkate et al. Invariant maintained here is lock and key will match as long as pointer is safe to access. For more details, please check our paper. Now let me walk you through the example step by step. For variables in memory, we store metadata in shadow memory. For simplicity, I'm just showing real value, posit value, and the pointer to the temporary. For variables in register, we store metadata in the stack. The first thing I'm doing in this program is dereferencing a pointer ptr1. In shadow execution, I'm going to access the shadow memory associated with ptr1 and load the real and posit value in metadata space in fuse stack frame. To initialize the pointer to the metadata of each operands, I need to access T28, which is a pointer to the temporary in the stack frame. If it is valid, then we copy metadata associated with the operands of T28. Otherwise, we initialize operands metadata to null. In this case, it is invalid, and that's why pointer to the metadata of each operand is set to null. Similarly, we load metadata for B from PTR2 and metadata for C from PTR3. Now I'm calling root count function. For details on how do we handle function arguments and return, please see the paper. In the root count function, we are creating a new variable T1. In shadow execution, we create metadata for T1 in root count stack frame. We do real computation with real value of B and store it in T1's metadata. We store the posit value, computed value, and pointers to the T1's operands metadata, which is B in this case. We do the same thing for T2, T3, and T4. After computing T4, we noticed that T4 has high rounding error. And T4's computed value is totally different than T4's real value. To diagnose the root cause of this error, we can traverse back following the pointers to the operand's metadata and investigate how the error was propagated. The first thing we have noticed that subtraction operation at T4 has error of 62 bits. That is, all bits are wrong. From T4, we can access the T1 and T3's metadata and notice that both of the operands have the error of 43 bits. We recursively traverse each node and construct the entire DAG, which help us to do the root cause analysis. We figure out that T1 and T3 have error due to loss of precision, and it is magnified in T4 due to catastrophic cancellation. Now we return from the root count function, and root count stack frame is deallocated. At this point, T5 metadata is storing a dangling pointer to T1 and T3's metadata. By checking temporal safety metadata, we can know it is unsafe to access these pointers. Hence, at this point, we won't be able to produce the tag of instructions. The user has to put breakpoint just before this execution point to produce the tag. This design of storing the constant amount of metadata in program stack and following it to get the tag makes POSIT-debug scalable with long-running applications. Since POSIT-debug is based on compiler instrumentation, it can be used with interactive debuggers like GDB. Paper has a lot of other details, and due to lack of time, I'm not going to talk about it. If you are interested, please see the paper. Now I'm going to tell you how we evaluated POSIT-debug. In our experiments study, we evaluated the reliability, usability, and scalability of POSIT-debug. We performed experiments with a lot of micro benchmarks, some of them from HubGrind test suite. We also tested with large spec benchmarks and our own codic math library. We detected a lot of numerical errors in all these applications. POSIT-debug helped in detecting and diagnosing the root cause of the errors in codic math library. My group found POSIT-debug useful, and we improved the accuracy of POSIT codic library by 10x. For performance experiments, we took applications from Polybench and Spec and ran them with POSIT-debug. We have used 256 bits of precision for shadow execution. Compared to the software version of POSIT, POSIT-debug introduces 12x overhead on average. With the software version of posits, POSIT-debug has low overheads, and we found it to be useful. Before I conclude, let me give you a quick overview of related work. Since posits are very new, there is not much support for detecting numerical errors with posits. There are two closest pieces of work in floating point domain, that is HubGrind and FPTalks. Both are Valgrind-based dynamic instrumentation too. Our work is motivated by HubGrind, but we have different design goals. HubGrind's goal is to generate expressions so that they can be rewritten using Hubby. To achieve this goal, they do generalization, which requires to store metadata proportional to the dynamic trace of the program. In contrast, we store constant amount of metadata per memory location and provides DAG of instructions for debugging purposes. To conclude, posits is a new attractive representation for reals which provide tapered accuracy. POSIT-debug enables you to find numerical errors and debug them in POSIT applications. The key idea is to keep the metadata constant to the amount of memory usage of the program. It provides back tracing in the active set of functions to produce the DAG for root cause analysis. We have shown the same ideas are applicable for floating point, and we believe both of these tools can help developers to debug and detect numerical errors effectively. Both of our tools, POSIT and floating point version, are available online. Please try it out and give us feedback. Thank you for your attention.
Okay, so Sangeeta, thank you for your talk. I will, I guess, so let's take questions. Sangeeta will answer them live. So again, you can ask questions using the raise hand button in the participants window. And I'll call them out. But while you all are getting your questions together, let me just ask one of my own, which is there any way that you could store some kind of intra-procedural information to know how values that the active stack frame is working on were computed earlier? For example, could you store some kind of references to the functions that they are outputted from?
I think it is possible, but it will again add some memory overhead to store that pointer. But it is a good addition to the current framework. It can be done. I think so.
Okay. We have another question from Theo.
Hey, Sangeeta. Just because you've built all this tooling, what were sort of the quintessential numerical errors that you were able to identify by sort of comparing a linear float with arbitrary precision to a posit arithmetic that wasn't quite doing it?
So the one kind of error, basically, the thing is that with posits, we see error with floating point and we see error with posit, but the same error is magnified in posit, and that is because of loss of precision. That is the one kind of thing we have noticed. Another thing is, since posit doesn't underflow or overflow to 0 or none, it rounds to min pos and max pos. So sometimes your application can saturate for min pos or max pos, and user will have no way to know that because it will look like a very just normal number, and there would be error will not propagate to tell the user that something has gone wrong.
So can I summarize that in when you're using values in the posit that are in the upper ranges where you have less discretization, you are seeing errors show up in posits that do not show up in linear floating point.
Can I interject?
Yeah, sure.
So effectively, the experiments that we did was we took existing floating point applications and transformed them to posits and tried to see what kind of errors that you see. And many of these applications are written with the necessity of infinity. Like, for example, they assume infinity is there, and then they make us write code with this assumption. And when you translate them to posits, it saturates, it produces some sane number, and the developer is sometimes like confused by the eventual results. Like,
that makes sense on the saturation piece, but the
second
super interesting. What's super interesting is to see the comments Sangeeta made with respect to error that comes in when posits have only a much smaller sampling of values in that range, right? Than a linear float would have.
Yeah.
So that would mean that the values in the application are at the extremes of the dynamic range.
So there are two things, right? One, what happens is float provides like uniform precision throughout. So there is a lot of compensation code that is written by a lot of developers, assuming like you will actually get the same behavior. And now you write it with full of posits, you translate it directly. What happens is posit provides tapered accuracy. You lose precision. And along with it, you have catastrophic cancellation, which amplifies the loss of precision even more. And this is like, so the bottom line that Sangeeta was alluding to is, it's not trivial to take a floating point program and just run it with posit data type. You will get like some counterintuitive results, like counterintuitive behavior. So you're not making the claim that, for this application, posit is better or float is better. If you take a floating point application and just convert it to directly use posits, you will see counterintuitive error. And this is where like this posit debug was really helpful to us. Like, why are we seeing this counterintuitive behavior?
Yeah, no,
okay.
Totally.
Okay, so I think we'll have to continue this discussion perhaps on Gather over lunch. It sounds like there's a lot to discuss. But we ought to move on to our next speaker, who is Hui Guo. So Hui, if you could start the recording and then share your screen. Okay, you're unmuted now. So if you could start the recording and then share screen.
Record. Wait, I'm looking for record. Okay. Perfect. My name's Hui Guo. I'm going to represent a joint work with Professor Cindy Rubio on error-inducing floating point input generation. This work will appear in X 2020 in July. First, what are error-inducing inputs? Error-inducing inputs are floating point inputs that trigger a large numerical error in the result of the program. To find a way to generate error-inducing inputs, we first examine how an error-inducing input triggers a high error. So we use a program that implements recursive summation as an example. This program takes an array as input. So we manually crafted an input array. This array can trigger a high error in this program. So in the first operation, it adds A3 to A2. The result is negative 98. And E represents the error in the result. In this operation, the value of A2 is rounded off. We consider that as a severe precision loss. The second addition adds negative 98 to 98. And this is a cancellation. After the third addition, the program computes the sum of all the elements as 1.1 times 10 to negative 15. And the error in the result is negative 1.2 times 10 to negative 15. This is a very large relative error. So our insight about generating error-inducing inputs is that we should explore the operations where precision loss and cancellation occur. We designed and implemented a tool, FPGing. It's an error-inducing input generator that uses symbolic execution. Specifically, it has three components. The first component is accuracy check injector. It injects the program with inaccuracy checks. The second component performs symbolic execution on the injected program and generate a set of inputs that maximize code coverage. And the third component measures error for each of the inputs to identify error-inducing input. So this tool is publicly available on GitHub. First, we describe our first component in accuracy check injector. So there's two checks in the injector. The first check for precision loss. For addition and subtraction operations, we compute the difference of the component of the two source operands. If the difference of the two exponents is larger than a threshold sigma in magnitude, then we consider that as a severe precision loss. To illustrate what does the threshold sigma represents, we use this figure to illustrate that. So each number in this figure is represented in the form of sign, exponent, and significant. And sigma here represents the number of bits that are discarded in the significant of one operand. Second, we check for cancellation. We compute the maximum exponent of operand 1 and operand 2 to the exponent of the destination operand. If the difference of the two is larger than threshold theta, then we consider that as a cancellation. So theta here represents the number of bits that are cancelled out in the significant of the two operands. So we create the inaccuracy check using the two formula. So basically, this in accuracy check will introduce 3 branches. One branch identifies precision loss cases. One branch identifies cancellation operations, and one branch identifies operations that are accurate. So because precision loss condition is contradictory to cancellation condition, so there is no overlap between precision loss cases and cancellation cases. Second, we present our second component, symbolic execution. So this module implements an algorithm that iteratively concretizes input variables and executes symbolic execution. So first, we perform a random search for base values of the input arrays. And then we partition the input array into 2 groups. One group contains the variables for concrete values, and one group contains the variables for symbolization. In the while loop, we concretize the input variables in concat walls, and we symbolize variables in symbol walls and perform symbolic execution. Here, we monitor the status of the symbolic execution engine. If it times out, then we reduce the symbolic variables by half. And if it terminates and generates a set of inputs to cover program passes, then we redistribute symbolic and concrete variables and continue the loop. So we evaluate, to evaluate FPGA, we compared with 3 other tools. First is a random input generator. Second, S3FP is the state-of-the-art error-inducing input generator. And third, CleFloat, a floating point symbolic execution engine. This is also the symbolic execution engine we used in FPGA. Our benchmark include 3 summation programs and 9 matrix computation programs in C and 9 statistic programs in JSL. As you can see, all these programs take multidimensional input data, such as arrays, vectors, and matrices. The third column and fourth column describe the number of symbolic variables and the number of concrete variables in the initial partition. Here's the results. So basically, on the x-axis, these are the benchmarks we used in the evaluation, and the y-axis represent the maximum error each tool can trigger in the program, and different color represent different tools. Here, specifically for CleFloat, it failed to trigger an error for any of the programs. As we can see that in most programs, FPGA triggers the highest error. There's 3 programs. None of the tool can trigger a high error. And there's 3 other programs. S3FP triggers the highest error. We guess the reason is that probably FPGA cannot trigger cancellation in these 3 programs. To summarize the results, first, out of 21 programs, random and S3FP, they can trigger an error in 13 programs, and CleFloat failed to trigger an error in any of the programs. FPGA triggers an error in 20 programs. Regarding to the magnitude of the error each tool triggered, FPGA triggered an error that is approximately 10 to the -6 on average. So it's 2 orders of magnitude larger than the state-of-the-art S3FP. To conclude, first we design and implement FPGA. And in FPGA, we formulated precision loss and cancellation. to enable symbolic execution for error-inducing floating point input generation. And we designed an algorithm that performs iterative concretization that manages the number of symbolic variables to scale symbolic execution. To extend FPTing for larger programs, there's two future directions. The first direction is to add more optimizations to further scale the symbolic execution. Second, a direction is to add a search algorithm that automatically identifies operations for inaccuracy check injection. Thank you.
Okay, thank you, Hui. If there are questions, please use the raise hand feature in the participants window. I see one from Ganesh. So Ganesh, go ahead.
Hi, Hui, nice talk. Two questions. One is, do you target conditionals in any specific way in the code because you have symbolic execution? And the second is, do you provide diagnosis info in the sense of which program paths caused the error, or only you report only the largest error? Thank you.
Okay, so first, I'm going to reply to the second question regarding to diagnosis information. Yes, we do have. So it's like we're going to specifically we're going to provide information about whether there's some operations they trigger a large precision loss or a cancellation. For example, there's so these are the inputs FPT find for recursive summation. So basically, in the first input array, we can print in the first operation. There's a R here represent precision loss. There's a severe precision loss, and so for the second addition, there's a cancellation. So developer can use this information to diagnose their program. For your first question, I'm sorry, I didn't get it. Could you repeat that?
No, if there are conditional branches in the program, in your input generation, do you bias the input generation towards either approaching the conditionals or evading the conditionals? There could be interesting choices there.
Yeah. Yeah. Currently, we didn't inject inaccuracy checks for conditional operations. But that's an interesting thing to do in the future. Yeah.
Unstable errors there also. Yeah, which is okay. Thanks.
Thank you.
Okay, so I see that there are still more hands up, more questions that members of the audience want to ask. So if you could please just add those to the thread that I started in the FPTalks channel on the Slack, and we can go and answer any additional ones that pop up there. So thank you, Hui. And we'll now have one final talk for this session by JP Lim, and his is also recorded on my computer. So I'll share my screen and play that now.
Hello everyone, my name is Jay Lim, and I'm a PhD student in Rutgers University advised by Santosh Nagarakate. It looks like nowadays everybody's creating their own representation. Hello, everyone.
Can people hear the sound? Okay, good.
My name is Jay Lim, and I'm a PhD student in Rutgers University advised by Santosh Nagarakate. It looks like nowadays everybody's creating their own representations for approximating real numbers. I'm not saying that it's a bad thing, but it means that we should have a math library for each of these new representations. So today I'm going to talk about our experiences in trying to create a math library for these representations. In the last few years, we saw a number of new representations for approximating real numbers being proposed. John Gustafson proposed a posit representation, which provides tapered accuracy, as you have seen from Sangeeta's talk. Google and Intel proposed bfloat16, which is a 16-bit floating point representation with 8 bits for exponent. And just a couple of months ago, NVIDIA proposed TensorFloat32, which is a 19-bit floating point representation with 8 bits for exponent. These representations are proposed for the applications in neural network and HPC, and as such, these communities are very excited about these new representations. However, because these representations are so new, there are no math libraries designed specifically for these representations. Because they're primarily used in numerical applications, it would be really great to have native math libraries for these representations. Now, one important requirement of a math library is that it should produce the correct value for all inputs. If the math library itself produces incorrect results, then any application using this math library will produce incorrect results, even if the rest of the application is numerically correct. So in this presentation, I would like to share with you the experiences we had with creating a correctly rounded math library for these new representations, the challenges in creating correctly rounded math libraries, and our solution to tackle this problem. So let me start off by first talking about what is correctly rounded math library. To illustrate, here's a number line in real numbers, and here are some consecutive bfloat16 values on the number line, and bfloat16 representation can only represent finitely many rational values. So you can't exactly represent irrational values like log 10 of 1.8, and you have to round them to a bfloat16 value according to the rounding rule. In this talk, we will use the round to the nearest, pi goes to even rule, so log 10 of 1.8 gets rounded to b1. So if the log 10 function in our bfloat math library produces b1 for log 10 of 1.8, we say that it produces the correctly rounded value, and if it produces the correctly rounded values for all inputs, then we say that the math library is a correctly rounded math library. But in the past, creating a correctly rounded math library has always been a difficult task, and let me show you why. In a high-level perspective, the most widely used method to create math library function for any transcendental function f of x is to first mathematically derive a polynomial approximation of f of x. This polynomial can be derived using minimax approximation techniques like Remez algorithm or Chebyshev polynomial approximations, but because p of x is an approximation, it will have an error compared to f of x. But this error can mathematically be bounded so that we can tell how much error we can expect. Once we derive p of x, the next step is to implement p of x using a higher precision representation than the target representation for the math library. For example, in our case, we're trying to create a bfloat16 math library, so we could implement a of x with doubles. And since a of x implements p of x using double, we're bound to have some error compared to p of x. Finally, we round the output of a of x to our target representation, bfloat16, but because of the error of p of x and a of x, we get the wrong result. So how small should be the window of error for p of x and a of x? To explain this, observe that given the value b1, which is our correctly rounded value, there is an interval, this gray interval around b1, where all values in this interval gets rounded to b1. Our log 10 of 1.8 value is also within this interval, and this is why log 10 of 1.8 gets rounded to b1. So for p of x and a of x, which approximates f of x, to produce b1 when rounded, the result of a of x has to be within this much of error from f of x, especially if the value of f of x is so close to the boundary of the gray interval. Otherwise, even the tiniest over-approximation to the right will result in a wrong result. And you can reason that if the f of x value is even closer to the boundary of the gray interval, the margin of error may be infinitesimally small. So are we doomed? Well, actually, let's take a quick moment here and think about what a correctly rounded math library means again. Our math library is a correctly rounded math library if it returns b1 when we ask for log 10 of 1.8. The goal of our math library is not to approximate log 10 of 1.8 as closely as we possibly can. Instead, the goal of our math library is to return b1 if the input is 1.8. Then what should be the goal of a of x? The goal of a of x should be to return a value within this gray interval we talked about, so that if we round the result, it rounds to b1. In other words, our a of x can return this value, this value, this value, or this value, and still the result will be correctly rounded to b1. And now our margin of error for a of x is significantly larger than what we had before. And this is the intuition in our approach, which was inspired from the minefield technique by John Gustafson. Our insight is that we should derive a polynomial approximation and its implementation a of x such that the result of a of x produces a value within this interval. Then the rounded result will be the correctly rounded value. So to this end, our approach in high level has two steps. First, we identify these gray intervals for the output of f of x for each input. This step is inspired by the minefield technique, but the minefield technique has to manually come up with the polynomial approximation. So instead, we generate p of x by using these intervals as linear constraints, and we use linear programming solvers to create p of x. So now let me explain our techniques a little bit more in detail using examples. First, given a function f of x that we want to approximate, we identify all input values in our representation and compute the correctly rounded result. For each of the correctly rounded result, we identify the interval such that all values in the interval rounds to the correctly rounded result. These intervals are basically a constraint for our polynomial p of x. In other words, our goal now is to fit a polynomial that crosses all of these intervals. So how do we create such a polynomial? We'll observe that these intervals basically define linear constraints on p of x. The output of p of x should be within these values for each of the inputs. Because they are linear constraints, we can create a linear programming problem in terms of trying to identify a set of coefficients of a polynomial that satisfies all the linear constraints. If we can find a set of coefficients, then we can generate a polynomial that produces the correctly rounded result for all inputs. So we can give this problem to an LP solver and solve for the coefficients. Now, if you have looked at math libraries, you will know that there's a lot more to a math library, like range reduction and input transformation and so on, and we have techniques to deal with them as well. If you would like to learn more about our techniques in dealing with range reduction, please feel free to email me and I will be happy to answer any questions. Going back to our technique to produce correctly rounded math libraries, we were able to use our technique and create approximation functions for a number of transcendental functions for bfloat16 already. Internally, the library uses double computation, and for all of these approximation functions, our math library produces the correctly rounded value for all inputs. During the evaluation, we also wanted to know what would happen if we approximate these functions by using the float math library. So we did an experiment where we convert the bfloat16 input into float, use float's math library to compute the result, and then round the result back to bfloat16. But what we found out was that there was a case where this produced the wrong result. This case is especially interesting because the float math library produces the correctly rounded result for float, but when we round this result to bfloat16, it became a wrong answer. So hopefully this result convinces you that it is important to create a native math library for each representation. Additionally, we were able to create correctly rounded approximation functions of a number of transcendental functions for 16-bit posit representation. And also, we were able to create an approximation function of log2 of x for a small input domain for the float representation. We are still actively creating correctly rounded approximation functions for other transcendental functions as well, so this list will grow larger. In conclusion, many exciting new representations for approximating real numbers have been proposed recently, and there is excitement in the neural network and HPC community to use these representations. However, these representations do not have native math libraries yet. So we present an initial effort to create a native math library for these representations that produce correctly rounded results for all inputs. Our technique generates a polynomial approximation of transcendental functions by approximating the correctly rounded result rather than the actual f of x values, and we were able to use this technique to create a number of correctly rounded approximation functions for various representations, such as bfloat16, 16-bit posit, and float. Thank you very much, and if you have any questions or comments, please do not hesitate to email us.
Okay, so thank you, Jay. Really exciting talk. Jay will be taking questions live, so I already see one hand up, and remember you can do the raise hand thing from the participants window. So Zach, questions?
Yeah, one thing I was curious about, if you look at a lot of math libraries, there's a fair amount of mixed integer float computation. Does that arise in your range reduction, or do you just not need it? Or, yeah, I'm just curious if you need to generate that kind of code.
I couldn't really understand about the integer part. Could you repeat that again?
So if you look at like a libim implementation, a lot of times the first thing it'll do is it'll basically cast to unsigned int, so it can then extract the fields and then operate in those fields either in higher precision or to do like range reduction carefully on the exponent. It tricks like that.
So typically, when I looked at the math library functions, the cast that they did from floating point to integers were mostly to optimize the functions itself, rather than to to do the approximation itself. So mostly what happens is first like all of these theoretical numerical range reduction techniques and polynomials are generated for real numbers first, right? And then afterwards they look at these functions and they say, oh, if I can optimize this code by converting it to integer and then trying to do some of the integer operations to speed up the process. For right now, our technique doesn't really, we haven't really gone through that part yet of optimizing the code itself. So everything is really done in double representation. And one of our future work is to actually take our functions and try to optimize it using integer operations and doing things like that.
Or maybe not. I wonder if actually you make verification a lot easier by avoiding this mixed integer floating point. There've been a couple of PLDI papers on why it's so hard to do that reasoning. So that's a strength of the technique. Yeah. Thanks.
So that was that's actually one of the challenges that we're going to have to face, is how do you make sure that this integer operations that we optimize actually does produce the correctly rounded results. Right? So yeah, you're absolutely right.
Okay, so we have another question from Hans Boehm.
So presumably a much less interesting implementation technique here is to compute these functions by table lookup. Can you say something about why you would or wouldn't want to do that? What the trade-offs are?
So some of the table lookup techniques that I know of is actually to split up this input domain into smaller input domains, so you can create a piecewise polynomial function for each of them. And that's something that we are going to do in the future to, especially for trying to create math library for larger representations like float. It might make more sense to create polynomial approximations for a really small input domain instead of the entire domain between 1 and 2 for approximating log, for example. Because in float, if you take all the float numbers from 1 and 2, there's about 100 million points, I believe. So it might make more sense to split it into smaller parts and do it that way for if you want to approximate a larger representation. But for our case, for 16-bit representations, we found that using table lookup was not necessary to produce a reasonably small polynomial that can approximate the input domain that we were interested in.
Thanks.
Okay, I know that people had more questions for Jay, and unfortunately, at least the formal end of the session is now, but luckily we can continue discussion over lunch, or I guess whatever meal you'll be eating wherever you are, in Slack or on the Gather. So I know that a lot of people checked out Gather over that first break, and I think, generally speaking, there's some good conversations had. So I'll see you all on the Gather in a few minutes, and maybe I'll pop out for lunch as well. So see you all there, and also see you in 2 hours at 1 p.m. Pacific time for the third session of FP Talks. See ya.